Hey everyone, this is question number 20 from chapter 13. So this problem asks us to find how much time is gained or lost in a year for a clock that's heated to 29 degrees Celsius when it keeps perfect time at 17 degrees Celsius. So I went ahead and wrote some notational things. In equations that I write, capital T is going to represent period, temp is going to represent temperature, and then we're told in the question stem that frequency dependency on length for a simple pendulum applies. So that is this equation here for period, T equals 2 pi square root L over G. Okay, so first thing we can do here is write out equations for the two periods at the two temperatures, okay? So your initial period T naught is going to be equal to 2 pi square root L naught over G, okay? And then your adjusted period T is going to be equal to 2 pi square root L over G. Okay, so this is for 17 degrees Celsius, and this is for the 29 degrees Celsius. Okay, so the first thing that we need to notice here is that T is going to be larger than T naught because L is greater than L naught. Okay, so with every swing of the clock, the heated clock will indicate that a time T naught has passed, but the actual amount of time that has passed is T. Thus, the heated clock is, quote, losing time by an amount of delta T equals T minus T naught every swing, okay? And the fractional loss is given by delta T over T naught. Okay, so with that equation, delta T over T naught, we can plug in these two equations and solve. Okay, so delta T over T naught equals T minus T naught, we just defined that as delta T, over T naught, okay? And we can plug in the formulas that we had earlier for the periods, 2 pi square root L over G minus 2 pi square root L naught over G, and that is all over 2 pi square root L naught over G. Okay, so first thing to note, 2 pi's in all of these terms, so that can cancel. And we are left with, so is over G, everything is divided by square root of G, so we're left with square root of L minus the square root of L naught over the square root of L naught. Okay, so then from here we can define that L is equal to L naught plus delta L. So we're just trying to put everything in terms of L naught here, minus square root L naught over square root L naught. Okay, so then now that we have a delta L, we can define that delta L in terms of the temperature expansion coefficient. So L naught plus alpha, L naught delta temp. Minus square root L naught over square root L naught. Okay, so now we could factor out L naught I'm going to go to another page. We can factor out L naught from that problem, and you get equals the square root of 1 plus alpha delta t, excuse me, let me stick with my notation, delta temp minus 1. Okay, so that's just pulling L naught out of that equation. Okay, so now we have this is equal to the square root of 1 plus alpha for brass, 19, times 10 to the minus 6 degrees C, times our change, delta temp, 17 to 29 is 12 degrees C, and then minus 1. Okay, so you plug all that in, and you get 1.1399 times 10 to the minus 4th. And that is equal to delta t over t naught. So this is delta t over t naught. Okay, so thus the amount of time lost in any time period t naught is delta t equals 1.139 times 10 to the negative 4th times t naught. Okay, so if you have delta t over t naught equals 1.1399 times 10 to the minus 4th, delta t, you can solve by multiplying t naught over. Okay, so for 1 year, we have delta t equals 1.1399 times 10 to the minus 4th times seconds in a year, 3.156 times 10 to the 7th seconds. All right, plug that onto your calculator, and you get delta t equals 3,598 seconds. And if you divide that by 60, you get about 60 minutes. So the clock loses about 1 hour every year.